We're going to start off with an exploration of all things Rootstock, and I'm going to welcome to the stage Raúl Laprida, who's going to take us into all the cool things that are going on in Rootstock and maybe even some new things coming out soon. Let's give him a big warm round of applause. Thank you.
Thank you, everyone, for joining the first session. I know it's early morning. Is it working? OK. Yes, it is. My name is Raúl Laprida. I'm Director of Architecture at RootstockLabs. And the idea of today is, first of all, give you an introduction to Rootstock in case you don't know us, and give you an overview of our main technological components. And then move on to the juicy part, which is the new protocols that we are working on right now. And that's basically BitBMX and the new trust minimized bridge designs that we're working on. So what is Rootstock? Rootstock is a sidechain. Basically, that's a blockchain, a standalone blockchain that has some relationships with Bitcoin. It uses proof of work to secure the blocks, just like any proof of work blockchain, for example, Bitcoin. It is an unsubsidized blockchain, meaning when a new block is created, there's no new native cryptocurrency being minted. So all the fees from the transactions are the actual block reward that the miners get. The relationship with Bitcoin is that Bitcoin miners actually mine Rootstock blocks through a technique called merge mining, which I'll explain later. And Rootstock is also smart contract capable, so you can run Turing-complete programs on-chain in Rootstock. And the native cryptocurrency of Rootstock, being a sidechain, is the one from the primary blockchain, which in this case is Bitcoin. And it's available in Rootstock through the two-way peg, which is our bridge, that allows you to move back and forth beacons from Bitcoin network to Rootstock and vice versa. That's what gives Rootstock value for Bitcoin, because it enables having DeFi and all the smart contracts capabilities with the underlying asset of Bitcoin on Rootstock. So let's talk about the main components of the Rootstock blockchain. Of course, the main component is the node, the reference implementation, which we call RSKJ. The J stands for Java implementation. It is open source. That's a repo if you want to contribute. It is backed by the RSK white paper. And then all the extensions and improvements are defined in the RSK IPs, very similar to what you find with the EIPs or the BIPs. They describe the new proposals, and if they are approved by the community, they get implemented in the reference implementation. You can also contribute with the RSK SP as well. What's the relationship with Ethereum? I mentioned we are smart contract capable. Actually, we run a virtual machine that is compatible at the opcode level with the EVM, meaning we run the same opcodes. They are exactly the same. They use the same inputs and have the same outcomes. They are a different implementation, but they work exactly the same. That means that all the tooling that you have for Ethereum compilers, they are going to work on Rootstock right away. So if you are an Ethereum developer, you are basically a Rootstock developer. We also have the compatibility at the interface layer. You know, when you interact with the node in Ethereum environments, you need to do it most likely through the JSON RPC interface. And this API, we are compatible as well. So if you have your application running on Ethereum, it is very easy to port it to Rootstock, because basically you just need to change some configurations, and it's going to work almost right outside of the box. What's our relationship with Bitcoin? I kind of introduced this, but you can see it as a two-way relationship. Bitcoin as the network, and Bitcoin BTC as the cryptocurrency. I mentioned we are a sidechain, meaning that our native cryptocurrency is the one from the parent blockchain. So we use Bitcoin, called RBTC in Rootstock, as our gas currency. Meaning that your transactions, when you pay for the gas, you pay with RBTC, which is exchangeable one-to-one with Bitcoin through the two-way peg. And then our relationship with the network, we actually extend the functionality through smart contract capabilities. And the miners, which are Bitcoin miners, through merge mining, they get the block reward, which is comprised of the transaction fees that the user pays with RBTC, which is basically BTC on Rootstock. Let's talk about the two components that I mentioned, which are merge mining and the bridge. So what is merge mining? Well, first of all, if you don't know what mining is, it is a concept that is related to proof of work blockchains. Basically, you have the miners, which are the block proposers. And in order to propose a block, they need to solve a cryptographic puzzle, which it's a double SHA function that they need to apply to the block header in Bitcoin, and they brute force it with a nonce. And the idea is there is a Bitcoin difficulty or a target number that they need to meet, and they need to try this function X amount of times until they get a result that is below the target. So if you expand this target as a number in bits, you would find that you need to find a solution that has X amount of zeros to the left, so a small number. And the way merge mining works is the miners, Bitcoin miners in this case, they are going to mine many secondary blockchains. That's why I say N is not going to be an unlimited, of course, amount of blockchains, which they call secondary blockchains because are additional blockchains that they are mining, but with the same proof of work effort. So at the same time, they are mining the blockchain block, the Bitcoin block, sorry, they are mining the secondary blockchains blocks. And the way it works is they need to get the ID or the block header, however you want to call it, of the secondary blockchains and add it in a specific place of the Bitcoin block. Once they do this, usually that's the Coinbase transaction. When they do this, they just try to solve the cryptographic puzzle as usual, and when they find the solution for Bitcoin, it's going to be also good enough to prove the proof of work of the secondary blockchains. That is because the secondary blockchains, they will have at least the same difficulty as the primary blockchain. In the case of Rootstock, which has a 30-second block time at the moment, the difficulty is slightly lower. So remember the number that I talked about with the 0 bits to the left? If Bitcoin has, I don't know, X amounts of zeros to the left in terms of difficulty or the target number, Rootstock is going to have 4 less bits. That's in comparison. So the set of possible outcomes of the hash is going to be a bit larger. So it's a bit easier to find the proof of work validation for Rootstock. And that's very mining pool friendly. Why is that? If you know how the mining pool works, it is a client-server architecture. Usually, if you are a solo miner of Bitcoin, you need to have a lot of hashing power if you want to win the block reward. And that's not the case for miners who don't have a lot of hash rate in their power. So what they usually do is they join a pool where they can contribute their hashing power, and in return, they are going to get a payment every month, for example, something that is constant, and they don't need to win the lottery of finding the proof of work solution of a block. And in this client-server architecture, the server is going to provide the reference or the header of the block that they need to solve, the Bitcoin block, and the clients, the miners, they are going to try to find this cryptographic puzzle solution. But the difficulty that they need to meet is usually lower than the one of Bitcoin. And why is that? Because this, which is called shares that they need to solve, they only exist for accountability purposes. It's the way of the pool to know how much hash rate they are contributing to the pool. And they get paid based on that. Of course, eventually, one of these solutions that they found is going to meet the Bitcoin difficulty. And that's the block solution that the pool is going to send to the Bitcoin network, and it's going to get the block reward. But it's not going to pay the miner who found it. It's going to pay, of course, the pool. The miner is going to get the same, a predictable payment every month or epoch. And that's how it works. The mining pools, we piggyback on that. Merge mining piggybacks on that. These shares that the clients are solving, if they are enough for the secondary blockchain difficulty, the pool is going to send it to relay to the secondary blockchain network because it solves the proof of work for the secondary blockchain block. And that's how they can mine more than one blockchain using the same proof of work, because we are piggybacking on the Bitcoin block proof of work. And they get, as a result, the block rewards of the secondary blockchains that they merge mine. And the secondary component is the bridge, which is, of course, very important. It is the way that we can move. Of course, we are not moving Bitcoins from the Bitcoin network to RSK and vice versa. We call it the puppet because of certain reasons that I'm going to explain. It is, in fact, a federated bridge, meaning there is a member of reputable entities that run a specific hardware module, which is called the PO HSM. It's a hardware security module, a tamper-proof device that keeps the cryptographic material required to sign the Bitcoin transactions for the pegouts, meaning when you want to move Bitcoin from Rootstock to Bitcoin again. They also run a Rootstock node that is highly connected, and those are the only two responsibilities of these members. They only need to have this connected to the internet and power on. They don't do anything else. Then, of course, on the Rootstock side, you have the bridge smart contract. It is a smart contract that runs on Rootstock, and is in charge of executing the peg-ins, commanding the peg-outs, and maintaining the federation as well when it needs to be upgraded. And it's called POPEG because, and I'm going to explain it with the peg-in and peg-out, so you do understand how it works. In the peg-in, a user wants to move Bitcoin to Rootstock, so it sends the Bitcoin to an address of the multisig that is controlled by this federation, and then the federation is going to inform the bridge smart contract about this peg-in, and the smart contract is going to give you the RBTC. But this is decentralized because you don't need to wait for the federation to inform the bridge. You can go yourself and inform the bridge, which means calling the smart contract in Rootstock, informing about your Bitcoin transaction that it's a peg-in. How does this work? Well, the smart contract in Bitcoin, in Rootstock, being Turing complete, it runs a Bitcoin wallet SPV. So you just need to prove with your SPV proof that the transaction happened in Bitcoin, and you get your RBTC. So it's completely decentralized. The other way, Rootstock from BTC, of course, it's not going to be fully decentralized because of the lack of capabilities of the Bitcoin scripting language. But the way it works is you inform the bridge about your peg-out, so you are giving your RBTC to the bridge, and the bridge is going to create the Bitcoin transaction, and one of the outputs are going to pay you, and then it is going to wait for a certain amount of proof of work to be built on top of your transaction. Once that happens, it's going to command the HSM devices to sign the Bitcoin transaction, and it's a certain threshold of HSMs sign the transaction, it can be relayed to the Bitcoin network, and you get your Bitcoins. And these HSMs, they are not dummy devices. They cannot be forged, and the transactions that they sign, they must come from the bridge smart contract. So it's not that the federator members, they can tell the HSM what to sign. So it needs to come from the bridge smart contract, because these HSM devices, they run a Rootstock SPV node, so they can verify the proof of work that the transaction has. So it has to meet this, and it's around 33 hours of proof of work. So it needs to meet the criteria, and it needs to come from the bridge, and then they are going to sign. So basically, the federators or the members, they cannot really attack the bridge. The only thing that could happen if in, I don't know, a catastrophic event where the majority of the HSMs go offline, and this is difficult because they are distributed geographically, but if it happens, the POPEG, the pegouts would stall. They would not happen because there are no devices to sign the transactions. In that case, we have emergency lock time wallets that would allow you, after a certain amount of inactivity of the bridge, to migrate the funds to a new POPEG. And of course, the devices, they have firmware attestation, and also they are audited by these members. So I kind of mentioned this already, and I'm trying to speed up because I want to talk about BitVM. You know, it's very easy to develop on Rootstock because of the opcode interface compatibilities. All the standards they are used in Rootstock. If they're used on Ethereum, they're using Rootstock. All the frameworks, for example, OpenZeppelin, they can be used out of the box. But there are some configurations that when you start developing, you start to notice, and I want to talk about them. There are just two. One is the derivation path. You know, when you have your wallet, you have your seed phrase, and you can always get the same private and public keepers based on that seed phrase. And it works with BIP, which is the way you derive your keepers from a seed. And you can think of it as, you know, the path when you go to the file system, and it's so words separated by slashes. That's a hierarchical configuration, and it's kind of the same. And one of these paths is the coin type, and it's unique for each blockchain. So for Ethereum, it's in mainnet is 60. For Rootstock, it's going to be another number, 137. So if you are using a wallet or a tool that needs to derive your wallet, your private keepers, and if it doesn't support Rootstock, you need to change that number. And it's going to allow you to do that. For example, MetaMask is going to allow you to do that. If it supports Rootstock, you don't need to do anything because it's going to know the coin type of Rootstock. And the same happens with the checksuming. Ethereum uses the EIP55, I think it is, which is the way the checksum is calculated. When you enter an address, if you use the lower and upper cases, you are checksumming the address, meaning that it's going to tell you if you have a typo. Since it uses only the address as input, it doesn't know about other chains. EIP 1191 is multi-chain, and it uses the chain ID also as input for the checksumming, and that's what we use. So if your tool doesn't implement EIP 1191, you have to either implement it, which is very easy, it's just adding the chain ID as input, or you need to stop using the checksumming, and you can do that by using lowercase addresses. But I encourage doing the first one. This is a very dumb example of how you would interact with a Rootstock node. The joke is that it's the same code that you would use on Ethereum, so if you are not going to see any difference. So yeah, it's very easy to develop on Rootstock. This is an overview of some of the ecosystem built on top of Rootstock. There are some players missing. For example, SushiSwap, I see it's not here, or the graph is also not here. But this is a good overview. And some numbers from Rootstock. So we are live with 100% network uptime since January 2018. So the days, maybe they need to be updated there. We have, on average, 60% of Bitcoin miners merge mining Rootstock, so that's a lot. So we also have one, on average, it's 20 seconds block time, and we are trying with new developments to take it to around 5 seconds with things like micropo, and also increasing the throughput with technologies such as parallel transaction processing. Down to the bottom, you can look at the amount of Bitcoin that is locked in the two-way pair. It's almost 3,000, and the amount of tokens that we have locked in DeFi protocols on Rootstock. And now to the good part. So I mentioned you a good use case actually for BitVM, which is the bridge, which is fully decentralized for the pegins, but it has some limitations for the pegouts, meaning that you need to have these members, that it's not an open membership, so you have some, even though it's the most secure bridge, you can have some reservations as a user. So BitVMX, one of the use cases solves that. So what is BitVMX? First of all, it's a iteration over a concept that Robin Linus introduced some months ago, which is BitVM for theoretical purposes only, which brings the disputable computation paradigm to Bitcoin. If you know about optimistic rollups, you basically know a lot about BitVM. So basically, it's executing off-chain a pre-agreed program, and then the outcome of that program is going to allow you to spend a UTXO in Bitcoin. And when you spend the UTXO, a lock time period starts, and after the lock time period is expired, you are allowed to spend the Bitcoins. Any of the verifiers of the protocol, they can challenge you with an on-chain dispute resolution protocol during that time. And that's how it works. So the happy path, when all the computation is correct and all parties are honest, you don't need to interact on-chain. So it's very convenient and very cheap. And you get your Bitcoins. So you can see with that it would be very useful for a bridge, because you can have as your program, the program that validates your pegouts in Rootstock, and you would try to spend the Bitcoins on-chain, and the verifiers, they are going to run the same program, and if it's okay, they are not going to challenge you, and you get your Bitcoins. So that's your pegout with BitVMX. And it has other uses, for example, snark verification. It's like the holy grail. We actually publish in mainnet Bitcoin our snark verification dispute resolution protocol yesterday. So we already achieved that. Basically, if you can Yeah, thank you. If you can create a program that can have a zero-knowledge proof, and you can verify optimistically that on Bitcoin, basically you can verify anything. So it's like, of course, having also the capability of having any type of off-chain program is more useful because you can focus on what you don't need scenario verification for everything. So it would be cheaper and more convenient to have both scenarios. And that's what we do. We actually, well, first of all, I haven't explained it, BitBMX, it emulates a RISC-V 32-bit core CPU. So basically, we have that implemented. So you have your program in whatever language you want. You compile it to an ELF binary, and then you feed it to the virtual CPU, which is a RISC-V, and the opcodes, they are implemented with Bitcoin script. And that's the fun part, because when you need to dispute one of the steps of the program execution or the state of the CPU, since it's written in Bitcoin script, you can go in Bitcoin and verify it there. And that's the good thing about having the CPU. So and here I'm explaining the process with two parties. You can extend it to n parties. This is a simpler one. You're going to have the parties agreeing on a predefined program that they want to run off-chain. One is going to be the prover or the verifier, or you can call them also the verifier could be the challenger of the watchtower. And the prover also in some contexts can be called the operator. The way the status of the CPU is created is using a hash chain. Basically, let me see if I have it here. Yes, that's the instruction specification of a RISC machine. So you have your inputs and your outputs. And when you are creating, when you execute the program, you get the execution trace. In order to know the state of the CPU, which is basically the status of the memory registries at a given time, we create a hash chain which is comprised of the hash of the previous step plus the the outputs of the current step. And with that, we can know the status of the CPU at any step of the computation. So the prover and verifier, they need to agree on the program. They need to create, and this is the complex part, a direct acyclic graph of all the Bitcoin transactions that are going to orchestrate the dispute resolution protocol in case it's needed to do it on-chain. So they need to pre-sign all these Bitcoin transactions. They are actually creating a stateful program in Bitcoin, which was unheard of before, because you cannot pass the state or information through Bitcoin transactions. But now you can. And how does this work? Well, there is a concept that we envision that is linked messages, which basically is this very simple protocol. It looks kind of scary, but basically you have a start transaction. In our scenario would be the prover trying to spend some Bitcoins. And if a challenge happens, the challenger is going to consume the UTXO, and it's going to add some data. Here is depicted with the X and the signature. And it's going to force you to consume this transaction with a response. The way it forces you is with a time lock. If that time lock expires and you haven't responded, the challenger can get your funds or your security bonds independent on the protocol. So you are forced to answer, assuming you were honest. If you were dishonest, eventually you are going to lose your funds because the challenger is going to win the dispute. But the idea is that with this protocol, you're going to go through that graph, direct acyclic graph of transactions that I showed before, in order to find the exact part of the opcode that was faulty or miscalculated by the prover. Also, the challenger could be dishonest, but that could happen. It's not going to win much because eventually, if one is honest, the protocol is going to go in favor with the honest party. So once they agreed on all the protocol, they need to submit the setup transaction to Bitcoin. Basically, they create this address where they put the funds. If it's a payout, it's the amount of funds that you are going to pay out if you execute the program of payouts. And then they are going to commit to this program. And that's it. That's how you start the protocol. If the prover doesn't want to spend the funds, you don't need to do anything else until the prover wants to spend the funds. When that happens, the prover sends the kickoff transaction, which was already predefined by both parties. Pre-signed, sorry. So in the happy path, here, example, the prover wants to do the payout. In the happy path, the verifier is going to find the input of the execution in the transaction, in the kickoff transaction, because the prover needs to feed the input of the off-chain execution program in the transaction that is trying to spend the funds. The verifier is going to run the execution off-chain, and if everything is OK, if it got the same result that the program passes OK, it's not going to challenge you because there's no way it's going to win if it tries to be dishonest. So the happy path, you get the funds after the time lock expires. The challenge path, the verifier found a difference in the execution trace, so it's going to consume the UTXO of the kickoff transaction with a challenge transaction. Basically, it's going to ask you for some information about the opcode that you run. And this is going to be an interactive protocol that is going to take some steps. The maximum steps were defined in the graph that I showed you before. And the idea is to find the step that was faulty and find the reason why, and to prove on-chain that you committed a fault. In this case, would be the prover. And when that happens, the prover loses the funds or the security bonds or whatever you're modeling. And if the verifier was the one who cheated, assuming there are security bonds in the protocol, it's going to be slashed and probably kicked out of the protocol. Well, here is the prover responding. As I mentioned, it has to do it, otherwise it's going to lose the funds. And this is the graph that we created for BitBMX. You can find it in our URL, bitbmx.com or .org, I don't remember. Basically, it depicts all the possible challenges that the verifier can do. And it goes from invalid memory reads, invalid program counter, a wrong execution of the opcode, etc. The use case that we are very interested about and we are creating design is for the trust minimized bridge, which is basically creating an improved version of our bridge. And the way it works, generalized for the N party scenario, you have N parties. One is going to be the operator. N-1, they are going to be the watchtower of the verifiers. When you are creating the bridge, and I'm going to explain the peg out process, which is the most interesting one. You as a user want to peg out some RBTC. You are going to send it to the request to the bridge smart contract. In Rootstock, the operator, the only operator of the protocol, is going to see your request, and it's going to give you in advance the BTC. So you're not going to have to wait for the whole protocol. And then when the operator is ready to do the actual peg out, and that's the kickoff transaction that I showed before, it's going to send that transaction to Bitcoin, expecting the BTC that they pay in advance. Of course, you pay a fee for using this bridge. They're going to send the Bitcoin transaction, and if it's not challenged by any of the N-1 verifiers, after the time lock expires, they get the Bitcoin. Otherwise, they need to engage in this dispute resolution protocol to prove either that they didn't lie and it is the verifiers miscalculating the proof, the execution, or if you were dishonest, as the operator, you are going to lose your security bond and you are going to be kicked out of the peg. And one of the N-1 watchtowers, one of them, they are going to become the new operator, and the bridge is going to be secure. You are not going to lose the funds locked by the bridge. That's all the technical stuff that I had to show you today, and I want to talk about the grants program that we have. It's allocating over $3 million USD in prices. The only thing that you need to have is an idea to build a protocol or a solution on top of Rootstock. You don't need to have it implemented. You just need to join and pitch the idea. And if it is a good idea, you're going to be have these incentives to take it to fruition. And you can have have the links down there. You can see them, and you also have the QR if you want to have all the information about Rootstock. And last but not least, we are having a meetup today at 5:30 p.m. If you want to join us, you can scan the QR code. And amazingly, we have 50 seconds for questions. If someone wants to ask something, you can ask about my sleeve. It's not weird at all. Yeah.
Hold on 1 second. Just make sure everyone can hear you. Ready? Here you go.
Can Bitcoin be applied to commodity stocks as well? Well, to avoid find a correct term, fraudulent purchases or anything like that?
I don't think I got your question, but with BPMX, basically, whatever you can model off-chain, and you can compile it to a general purpose CPUs as RISC-V, you can verify it in Bitcoin, and it's going to trigger a transaction in Bitcoin. So without any financial background, I can tell you that wherever you can model like that is going to work with Rootstock and being executed on Bitcoin.
And in real time.
What do you mean by real time?
Like, for example, if I use the Bitcoin to buy some commodities, and at the last second, if a commodity decides to go nosedive, I can retrieve the Bitcoin, within seconds before I lose everything.
So the Bitcoin block is 1 every 10 minutes, so you cannot have like micro instructions in Bitcoin. If you work with Rootstock, which is Bitcoin in a sidechain, you can have more granularity because the block time is even less. It's 30 seconds, and it's going to be 5 seconds. You have more resolution there, but you cannot do that directly on Bitcoin because it's not built for that.
Any other questions? What is the story of your sleeve?
So yeah, so I'm trying to remove a tattoo with laser tattoo removal.
Oh, okay.
And
all right.
one day before the flight, I told the technician that I wasn't seeing any results. So she really went in and really messed up my arm. So yeah, I need to cover.
All right. Thank you for that. Thank you, Raúl, for sharing that detail and also all that great stuff before it. Thank you.